Okay, so this is Wednesday's homework, 7.5, 7.56, 7.65 and 7.68. So 7.55 is a Rydberg equation problem, and it reads, what is the wavelength of the photons emitted by hydrogen atoms when they undergo a transition from n equals 4 to n equals 3? So it's always worth sketching it out. This is 55. N equals 4 to n equals 3 falls down there, radiates some light. And what do we know? Well, it's ending in n equals 3, so that means that the wavelength is going to be in the IR, so it means that it's going to be greater than about 750 nanometers. Okay, so 1 on the wavelength is going to be given by the Rydberg equation, R 1 on n 2 squared minus 1 on n 1 squared, and n2, it's always going to be less than n1. Okay, so where it ends up is always going to be lower than where it started. We actually want the inverse of that, r 1 on n2 squared minus 1 on n1 squared to the minus 1 there is going to give us the wavelength. Okay, so now we've just got to put all of our numbers in, right? Wavelength equals 1.10 by 10 to the 7 meters to the minus 1, 1 on 3 squared minus 1 on 4 squared, and the whole lot to the minus 1. Really very fuzzy, this camera, for some reason. I have to try and work on that to get it cleared up. Okay, so lambda equals, let's put all of this into the calculator. 1, turn the calculator on, 1 exponent 7 times parentheses 1 divided by 9 minus 1 divided by 16, close the parentheses, equals to the minus 1, 2.06 by 10 to the minus 6 meters. 2.06 times 10 to the minus 6 meters. We can turn that into nanometers if we want, times 10 to the 9 nanometers per 1 meter. Let's see if we got it right. Times 1 by 10 to the 9, 2057 nanometers. Sure is greater than 750. Let's just double check that I got everything right. 1.1 exponent 7 times 1 divided by 9 minus 1 divided by 16. Close the brackets. Take the inverse. Error. Somewhere there is an error. Okay. Well done for checking that. 1.87. Okay. So that means that it was 1870 nanometers. Probably worth checking again just to be sure. 1.1 second function e to the 7 times brackets 1 divided by 9 minus 1 divided by 16. The whole thing to the minus 1. Yep, definitely 1.87 by 10 to the minus 6. Okay, so we caught that error there. Well done. Okay, so that's 55. 56 is not a lot different, but it's asking you for a frequency. And in this case, 56, it reads, what is the frequency of photons emitted by hydrogen atoms when they undergo a transition from n equals 5 to n equals 3? So you're going to go n equals 5 down to n equals 3. Now, it's ending in n equals 3, so we know that lambda has to be in the IR, that is, has a wavelength greater than 750 nanometers. And if we think about it here, n equals 4 is down here. So this photon that is emitted is going to have more energy than in 55 in the case above. So its wavelength is going to be shorter than that. So its wavelength is going to be greater than 750 nanometers, but it's going to be less than 1870 nanometers because it's going to contain more energy. The other thing to keep in mind is that they ask for frequency, not a wavelength. So I'll calculate the wavelength and then I'll turn it into frequency. So lambda equals 1.10 by 10 to the 7 meters to the minus 1 times by 1 on, and the smaller of these ones, 3 squared minus 1 on, 5 squared, and the whole thing to the minus 1. Okay, so let's put that into a calculator and hopefully we'll not make an error. 1.1 by 10 to the 7 times 1 divided by 9 minus 1 divided by 25, close brackets, the whole thing to the minus 1. And I got 1.27 or 28 times 10 to the minus 6 meters, which is a shorter wavelength than what I got in the case up there. So I'm feeling happy about that. Going to turn it into nanometers, 1 e to the 9. So lambda equals 1278 nanometers, and that sure as heck is greater than 750. So it falls where we wanted it to, right? It's less than 1870 nanometers and it's greater than 750. So I feel pretty confident that I got the answer right here. Okay, good. All right. So next we've got 65 and 68. So here we go. 65. So 65 reads, calculate the wavelength of the following object. So it's going to be a de Broglie wavelength problem. So it is H on mv. The only thing that to keep in mind about here is m is in kilograms. That's the only thing you have to take care of. Other than that, it's all easy going. So your first problem is a muon, which is a type of subatomic particle, and it has mass 1.884 by 10 to the minus 25 grams, and its velocity is 325 meters per second. So first of all, I just need to convert my mass into kilograms. 1.884 times 10 to the minus 25 grams times 1 kilogram is 1,000 grams, so that gives me 1.884 times 10 to the minus 28 kilograms. So my wavelength is 6.626 times 10 to the minus 34 joules seconds over 1.884 times 10 to the minus 28 kilograms times 325 meters per second. Now the thing to keep in mind is 1 joule equals 1 kilogram meters squared second to the minus 2. So Planck's constant has units of joules seconds, so that's going to have units of kilograms meters squared second to the minus 1. Okay, so 6.626 times 10 to the minus 34 kilograms meters squared second to the minus 1 divided by 1.884 times 10 to the minus 28 kilograms times 325 meters per second. So your per seconds cancel out, one of your meters cancels out, and your kilograms cancels out, leaving you with meters. So we know we got our equation right. So lambda equals, and let's just put this in the calculator, 6.626 second function e to the minus 34 divide, and this is important, on the bottom line here, because we've got more than one thing, we need to make sure that we put parentheses, 1.884 second function e to the minus 28 times 325, and I got 1.08 times 10 to the minus 8 meters. okay? And if you wanted to, you could turn that into nanometers. And lambda is 10.8 nanometers. Now that makes sense because the wavelengths of particles are normally much smaller than the wavelengths of visible light. And that's why we use electron waves in an electron microscope to view objects, because, well, the wavelengths are smaller and we can see finer features. Okay, so we've got 4 of these to do in 65. So let's move on to 65B. And in this case, it is an electron moving at 4.05 by 10 to the 6 meters that we have to figure out the wavelength for. So lambda equals h on mv, 6.626 times 10 to the minus 34, and the mass in it's 1.8, sorry, mass of an electron is not that, it's 9. Just going to abbreviate, 11 times 10 to the minus 31 kilograms, okay, and its velocity is 4.05 times 10 to the 6 meters per second. Okay, so its wavelength will be, and Planck's constant has those units. Put this calculator under here, 6.626 second function e minus 34 times, or divide, parentheses, 9.11 second function e to the minus 31 is the mass of electron, times, and its velocity was 4.05 second function e to the 6, close the parentheses, and I got 1.795 times 10 to the minus 10 meters now. Is that right? Okay, let's just write that down. 1.80 times 10 to the minus 10 meters. I'm going to double check that. 6.626 second function e to the minus 34 divide brackets 9.11 second function e to the minus 31, yep, times 4.05 second function e to the 6, close the brackets, 1.7958 by 10 to the minus 10, so it looks good. Alright, we can convert that to nanometers if we want, times 1 second function e to the 9, and it turns out to be about 0.2 nanometers, 0.18 nanometers. Okay, and we know that we're expecting that it's going to be less than the wavelength of visible light, so that seems reasonable. Now, you don't have to convert that to nanometers. I just did to bring it into more familiar terms. Alright, let's get a fresh piece of paper and do C and D. 65C, asking you for the de Broglie wavelength of an 80 kilogram athlete running a 4-minute mile. So a 4-minute mile, how fast is he going? So velocity is distance over time, and we want our velocity in meters per second. 1 mile is 1,609 meters. You need to look that up in a table. And the time is 4 minutes. So 4 times 60 is 240 seconds. So this guy is running at 1609 divided to 40, 6.70 meters per second, okay? Alright, so we've got his velocity. His mass is 80 kilograms. Well, that's nice. We don't have to do any unit conversions there because I've given us his mass in kilograms, and lambda is h on mv. So 6.626 times 10 to the minus 34 kilograms meters squared per second divided by 80 kilograms times 6.70 meters per second. So lambda is 6.626, second function e to the minus 34, divide brackets 80 times 6.7, close brackets. He's got a tiny little wavelength, 1.23 by 10 to the minus 36. 1.24 times 10 to the minus 36 meters, right? We know it's meters. That meter cancels out there, that per seconds cancels out there, that kilogram cancels out there. It leaves one of our meters behind. Okay? So there we go. He's tiny. His wavelength is tiny, smaller than him. We're not going to observe that. Okay, what's the wavelength of the Earth? That's the next question. D. Here we go. And it says Earth has a mass of 6.0 by 10 to the 27 grams, which is 6.0 by 10 to the 24 kilograms. That's the mass, okay? And it says it's moving through space at 3.0 by 10 to the 4 meters per second. That's its velocity. So wavelength equals h on mv, 6.626 times 10 to the minus 34 kilograms meters squared per second. Mass is 6.0 times 10 to the 24 kilograms, and velocity is 3 by 10 to the 4 meters per second. Okay, leaves us with one of the meters remaining. So put this into my calculator, see what I get. And we got 6.626, second function e to the minus 34, divide brackets, and our mass was, it's hard to see that on the calculator unless it's in the middle there, 6 by e to the 24 kilograms, and its velocity was 3 by e to the 4 meters per second. Okay, we get 3.68 by 10 to the minus 63 meters. So its wavelength is tiny. 3.68 by 10 to the minus 63 meters. Itty bitty. You know, basically not worth worrying about. Okay, smaller than the smallest subatomic particle. All right, so that's 65, and we've got one left that we were asked to do, and that was 68. And 68, here we go. So it says, how rapidly would each of the following particles be moving if they all had the same wavelength as a photon of red light? So if they all had a wavelength of 750 nanometers. Okay, here we go. So A, it's an electron, and it has mass 9.11 by 10 to the minus 31 kilograms. So lambda equals h on mv, and we've got to solve for what velocity is. So h on lambda so it's just going to be like that, isn't it? Yeah. That's it. Okay. So 6.626 times 10 to the minus 34 kilograms meters squared per second divided by, and our wavelength was 750 by 10 to the 9 meters, and our mass is in kilograms, so it's 9.11 times 10 to the minus 31 kilograms. All right, let's see what we got here. Meters goes, one of the meters goes, kilograms go, kilograms go. So it leaves us with meters per second, which is what we wanted for velocity. So V equals 6.626, second function e to the minus 34, divided by 750 e to the minus 9, it should be minus 9 meters, times 9.11, second function e to the minus 31. Put the whole thing in parentheses, it looks like that. Alright, enter. 969.78 meters per second. 969.78 meters per second. Probably should think about sig figs. In the problem you were given to 5 sig figs, and that's what I've given there, but I kind of rounded off a little bit. You probably shouldn't do that. Okay. All right, the next one, B, it's a proton. Okay, so a proton has mass equals 1.67 times 10 to the minus 27 kilograms. And so now we've got to figure out its velocity. Velocity equals h on m lambda. We did that rearrangement before. 6.626 times 10 to the minus 4. Let's put the units in just to make sure that we're on the right track. Its mass is 1.67 times 10 to the minus 27 kilograms, and its wavelength is 750 times 10 to the minus 9 meters. Don't forget the parentheses when you've got more than one moving part, more than one thing on the bottom line. Okay, the units, kilograms, kilograms, meters, cancels out one of the meters, leaves us with meters per second, which is great because what we're after is a velocity. Put it all into the calculator. 6.626, second function e to the minus 34, divide, don't forget the parentheses, 1.67, second function e to the minus 27 times 750 e to the minus 9, and I got a really small number. Okay, I got 0.529 meters per second. Now, does that make sense? Let me have a look here. 6.626, second function e to the minus 34. Divide brackets 750, second function e to the minus 9 times 1.67, second function e to the minus 27. Close the brackets. Well, I got the same thing twice. Let's just double check my math. Minus 27 plus minus 9. And that's going to give me minus 36. So then I would have something 10 to the minus 34. Yeah, it's plausible. Okay, that sounds about right. Okay. So it's worth checking that one in the back of the books. We can't because it's an even one. But I think it's right. It looks good. Alright. C, a neutron has mass similar to a proton, 1.67 by 10 to the minus 24 grams. So mass is 1.67 by 10 to the minus 27 kilograms. Velocity is given by h on m lambda, 6.626 times 10 to the minus 34 divided by 1.67 times 10 to the minus 27 times 750 by 10 to the minus 9. Oh, look at that. It's going to be identical to what we had before, isn't it? Okay, not surprising because protons and neutrons have basically the same mass. So that guy's going to come out 0.529 meters per second. We don't need to run through that calculation. All right, the last one is, it just says a particle, and it gives a kind of a mass for it, but it doesn't say what the particle is. So, there we go. So 68D, and it just says a particle that has mass 6.64 times 10 to the minus 24 grams, so 10 to the minus 27 kilograms. We can do kilograms to grams in our heads now. Okay, the velocity is h on m lambda, 6.626 times 10 to the minus 34. 34, yes. Kilograms, let's write it out, meters squared per second, just to make sure we're on the right track. Its mass is 6.64 times 10 to the minus 27 kilograms. And its wavelength is 750 times 10 to the minus 9 meters. That goes, kilogram goes, leaves us with meters per second. So confident about our formula. 6.626, second function e to the minus 34, divide brackets 6.64, second function e minus 27, times 750, second function e minus 9. Okay, and I've got a velocity of 0.133 meters per second. Okay, not very fast. Does it make sense? Well, this particle, this alpha particle, which we'll find out what they are later, is much heavier than a proton. It's about 4 times heavier than a proton. And it's going about 4 times slower and has a similar, to have the same wavelength. So it kind of makes sense to me. Alright, so that was Wednesday's homework complete.